So in the last video we talked about what a vector was and magnitude and direction of a vector, how to understand those things. And today we're going to focus on unit vector notation. In this video we'll focus on unit vector notation. But before we do, I'm going to kind of show you why it's even important. So here we have a two-dimensional vector, okay, but all of our physics, all the equations we know how to do, all the analysis we know how to do can only work in one dimension. And so what unit vector notation allows us to do is to take two-dimensional vectors and turn them into one dimension, okay? And so if you have this person right here that's looking, let's say this is a displacement vector of about, we'll say 5 meters, okay? This person that's looking at it, they don't see an object that's 5 meters long, okay, because it's moving, it's kind of pointed away from them, and so what they see is really about this long, and we'll say maybe it's like 4 meters long. Okay, they see it's kind of like, we'll call it projection of it. Okay, we'll see like this part of it. They don't see the whole length, they just see it looking like this. And another way you could think of it is if there was like a light shining down here. Okay, and this is like the shadow from this, and it's called the projection. That's why it's called projection. It's like as if you shine a light directly above it, it would be the shadow shining down here. And the same thing could happen like for a person standing over here. It doesn't appear 5 meters to them. It appears actually a lot shorter. To them it only looks like it's 3 meters. Okay? And if we were to shine a light like this, okay, the shadow here would be 3 meters tall as opposed to 5 meters. Okay? And so this vector, this two-dimensional vector, has one-dimensional components or projections that are 4 meters and 3 meters long. So one of the more interesting things here though is that this makes sense when we're talking about displacement, but this applies to all kinds of vectors. So let's say this was a velocity vector. So let's say we're kind of go with the same thing we got here. Let's say that we have an object that's going to travel 5 meters, but let's say it's going to travel that 5 meters in 1 second. So this is a velocity vector, 5 meters per second. Well, if we're watching, this person here is watching it move across, it doesn't look to this person like it moves 5 meters, it looks like it moved 4 meters. So this person sees as if it moved 4 meters per second. From the point of the projection, the shadow is going to move across this horizontal axis at a speed of 4 meters per second. So even though the object's going 5 meters per second, the shadow is moving 4 meters per second. Okay, or over here, we see that this person sees it, thinks it's only going 3 meters in that 1 second. So to them it's like it's going 3 meters per second. Okay, and if you were shining a light on it to project the shadow onto this axis right here, it would look as if the shadow was traveling 3 meters per second. These projections or these viewpoints, we call them components of this two-dimensional vector. It's got a horizontal and vertical component. We can actually slide them around, so we can take this one right here and move it over here to turn it into like a three-dimensional, or like a right triangle here. And then by Pythagorean theorem we know that this has to be 5 if it's like a 3, 4, 5 triangle. Okay, and so we can talk about a vector as its magnitude and direction, or we can talk about it as the two components or the two smaller sides of a right triangle. So now let's talk a little bit more about components. I'm going to show you why unit vector notation is important. Okay, so remember we can look at it like the thing that the people standing off to the side are going to see. Okay, and so let's say that we want to find what those projections are. Okay, well the way that we find this projection, okay, there's a mathematical tool for that, because whenever you use trig function sine and cosine, you're actually finding projections. Okay, so this horizontal projection we'll call x. Well, this is the adjacent side, so we say SOHCAHTOA, right, the adjacent over the hypotenuse of 12 meters going to be equal to the cosine of the angle 30. Okay, so that's going to say that x is going to be equal to 12 meters times cosine of 30. And when we do this multiplication here, we're taking 12 meters at an angle of 30 and we're projecting it onto the x-axis. Okay, and when we do that projection, we get a value of about 10.4 meters. Okay, and we'll do the same thing for the vertical axis. We're going to project it there using, this would be the opposite side if we put this right here. Okay, so instead to solve for y, we're going to use opposite of our hypotenuse is equal to sine of 30. Okay, so y, the projection for y would be equal to 12 meters times sine of 30, or 6 meters. Okay, so from here, now we want to write this vector out. When I write it out, we'll call this vector, we'll call it r. We're going to say that r is equal to 6 meters. Actually, let's put the x1 first. Okay, so we're going to say 10.4 meters plus 6 meters. Now, this is where we run into a problem, because this vector is not actually 10.4 plus 6. That would be 16.4. It's not that big. Okay, it's only 12 meters long. But we have to have a way of writing it out as a combination of these two, but also showing that these two are in separate directions. And so what we use is something called unit vectors. Okay, and so we have I here, which represents basically like a vector of unit 1 along the x-axis, and we scale it by 10.4. Okay, and then we have j for the vertical one, and this represents a vertical vector of unit 1 that we're going to scale up and down the vertical axis. Okay, and that solves our problem, because now these can't be combined because they're no longer like terms, and it's also a way that we can organize our horizontal components with our vertical components. Okay, this is a typical notation that's used. It's not something that it's necessarily that we're like nailed down to, but this is the way that it's traditionally written for vectors. Okay, this is called unit vector notation. We're going to analyze this velocity vector. We'll call it vector A, and it is 10 meters per second, and it's 40 degrees south of west. Okay, and so what I want you to do, just kind of like we did with the last vector, I want you to write it in unit vector notation. Okay. Okay, so to get the horizontal component, we're going to multiply 10 meters per second times the cosine of 40 to get that horizontal projection. And for the y component, we're going to do the same, but we're going to multiply instead by sine of 40 to get the vertical projection. Okay, and this is what we get. However, this is not the same as that vector. Okay, and I'll show you why. If we go ahead and draw this, okay, well, positive I is this way, and positive j is this way. Okay, and so we've actually drawn this vector, which is the exact opposite. So what it's going to be really important when we're drawing vectors and we're finding components is to kind of sketch it out, okay, and understand which way it's going. And so we're going to say that left is negative and down is negative. So both these components are actually negative. Okay, and there we have vector A. Okay, so the last thing we're going to do here is we're going to look at taking a vector that's written in unit vector notation and writing it in magnitude direction notation. And so here's vector B, and vector B is actually an acceleration vector. Okay, and so we're going to go ahead and take this acceleration vector and turn it back into magnitude direction notation. So the first thing we'll do is we'll sketch it, 4 meters per second squared in the I direction, and then we have 2 meters per second squared in the negative j direction. Okay, so we want to find this vector right here. Okay, so I've gone ahead and drawn it here so that we have an idea of what it looks like. Okay, and so the next thing we're going to do is we want to find the magnitude of this. So how would you go about finding the magnitude of this, the length of this vector? Well, it's at the right triangle, so we use Pythagorean theorem. So the square root of 4 squared plus 2 squared is going to give us our result. Okay. So we punch this in and we get 4.47 meters per second squared as the magnitude of our acceleration vector. Okay, and then so we say, okay, vector B has a magnitude, and actually one of the ways you write a magnitude is using these brackets here. So we'll say vector B has a magnitude of 4.47 meters per second squared, and has a direction which we still need to find. So we need to find this angle so we can say what direction it's in. How would you go about finding that angle? We're going to want to use inverse tangent, okay? And we'll say tangent of that angle is going to be equal to 2 over 4, okay? And so that would be inverse tangent is equal to, sorry, theta would be equal to inverse tangent of 1/2, or 2 over 4, which simplifies to 1/2. Okay, and so that when we punch that in, we're going to get, let me bring it up. We're going to get 26.6 degrees, okay? And so when we write it out, 26.6 degrees, and it looks like it is south of east, or since we don't have really a clear reference like where this is, we could also say below positive x. Okay, so both these would be okay here. Alright, so there you have it. Really quick, one thing I forgot to mention though, whenever I'm drawing these vectors, I always start with this horizontal component first, and then I draw this vertical component. And so that's the reason why we're always measuring of east here. So south of east, north of east, south of west, north of west. It's because we're always drawing this one first. Okay, and so to wrap this up, we're actually going to go ahead and do, I'm going to give you one more to practice this on your own. So we have this vector here, vector c, which is a velocity vector, and I want you to find the magnitude of c and the direction of c. So you're going to start by writing it out in components, 5 meters per second for I, and then it's positive 12, so I ran out of space here. So 12 meters per second for J. I want to find the magnitude, so it's going to be the square root of 5 squared plus 12 squared. Okay, you might recognize this as Pythagorean triple, and so we get 13 meters per second as our magnitude. Then for our angle, we're going to say the tangent of theta equal to 5 over 12, or sorry, 12 over 5. Okay, so that theta would be equal to the inverse tangent of 12 over 5, and then we can go ahead and punch this into our calculator, and we're going to get about 67.4 degrees. Okay, 67.4 degrees, and we could say this is north of east or above positive x. Okay, all right, there you go.